I know this is a repeat of some of the things that we've talked about already, but I wanted to provide the rest of the information here for frequency and correlates to frequency, especially considering simple harmonic motion. So again, the learning objectives are to determine frequency and its correlates and to be able to measure the wavelength of any frequency. The key concepts today are frequency, wavelength, and velocity. And just a refresher about the relationship that is shared between frequency and period. The number of complete vibrations in a time period, which is usually seconds, so time period is almost always in seconds, is the frequency, and the measurement is cycles per second. But we can also, I think we've discussed this before, use hertz. Okay, so cycles per second plus hertz equals the same thing. Okay, so the time component in frequency is almost always seconds. Period is the time that it takes to complete one vibrational cycle. So the period is always 1 over the frequency. Period and frequency share an inverse relationship, which means that as the frequency increases, the period decreases, and as the frequency decreases, the period increases. It's important to keep in mind that when frequency is described in hertz, the period is always calculated as seconds. The range of frequencies, I know I spent some time talking about this, but just to refresh your memory, 20 hertz to 20,000 hertz, which is a very broad range of frequencies, is the range of frequencies that humans can respond to. We may not be able to hear them all, or it may take a lot of intensity for us to just begin to hear those frequencies, but that is the range of hearing for humans. The speech range, which is characterized by this speech banana here, is 250 hertz to 8,000 hertz. Still a pretty broad range of frequencies, but these frequencies are the area where most of the speech sounds fall. And then finally we have the critical speech range, which is an even smaller range of frequencies that is called the critical speech range, and that's in here where the majority of frequencies lie. The sine waves of some frequencies. At 20 hertz, we can still look and count these frequencies. We can count the compressions and rarefactions to get the total number of frequencies. So we can easily do that from frequencies 1 through 20. But as soon as we start getting more than that, it's very difficult to draw and show those cycles. So it would be very difficult at this 80 hertz tone to try and count the compressions and rarefactions because it's so close together. So the higher the frequencies get, the more difficult it is to draw and show the cycles. Some examples of sound. So this is a piano note at middle C. And then here's a high C. Okay. So when you heard the one over here, the middle C on the piano is 262 hertz. And the highest note that we heard over here is 4,186 hertz. Okay? So there are several octaves between the middle C and the highest C on the piano. So that gave you an opportunity to hear two frequencies. Some of you may feel like you heard the lower frequency better, and some of you may have felt like you heard the higher frequency better. Really, our ears in that speech range and in the critical speech range, we hear them not equally, but we hear them better than any of the other frequencies in our range. The reason for that is the wavelength. Okay, so the wavelength of any frequency is drawn from one point on one wave to the same point on the next wave. Basically, when we're looking at lower frequencies, those lower frequencies have really long wavelengths, and those higher frequencies have really short wavelengths. So the size of the frequency measured from one point on one line, on one wave to the same point on the next wave is referred to as wavelength, and the symbol for wavelength is lambda. Wavelength is also proportionally related to frequency. Oops, sorry. Okay. So here we can look at the wavelength. We have 2 cycles per second here, or 2 hertz. And when we measure wavelength, we measure it, and it's usually easiest to measure it from the peaks or from the troughs or valleys. So this is the peak amplitude and this is the trough amplitude. So it's easiest to measure the wavelength from the peak of one to the peak of the wave next to it. Okay. So wavelength, or lambda, is the distance between the two. Again, lower frequencies have very long wavelengths, and higher frequencies have very short wavelengths. But wavelength is also dependent on velocity. So sound velocity is another concept. And earlier we talked about the different types of mediums. And those mediums are solid, liquid, and gas. The difference between those mediums is the closeness of the molecules or the particles that make up the medium. Okay? So in a gas medium, the particles are spread far apart, right? And they are bouncing all over each other and bouncing all around until a force is applied to them. A liquid is contained in a container, and solids are pretty solid and don't move a whole lot. But basically, the mediums are defined by how close or how far apart their molecules are. So that's why they're different. Gas molecules far apart, solid molecules really close together. So what does this have to do with velocity? Well, what is velocity? Basically, velocity is the speed of sound. Okay, so velocity is how fast sound moves through any type of medium. Okay, so we know that sound can move through a solid, a liquid, and a gas. But what we don't know yet is how fast sound moves through there. So the technical definition of velocity is the measure of how fast something in particular, in this case, the molecules that are moving in a particular direction. It's how fast they're moving. Speed is only one part of velocity, and direction is the other part. So velocity is equal to displacement divided by time. So I'm not going to expect you to understand or know how to calculate velocity because it's already been calculated for us. And so in a gas medium, and I've highlighted it here, the speed of sound is 340 meters per second, or 1,125 feet per second in air. I like to use the feet per second because I'm used to doing that, and I've been using this scale for many years. When I was a kid, we were supposed to be adopting the metric system in elementary school, but that never happened. And here we are some 40 years later, and we still don't use the metric system like the rest of the world. Okay. When I ask you to do calculations, I really don't care whether you do the calculations in meters per second or feet per second. They're equivalent measures. Then we have the speed of sound in water, which is 1,481 meters per second, or 4,859 feet per second. You'll notice how much quicker sound travels through water, right? So we're looking at 340 meters compared to 1,481 meters. This is almost 5 times as fast, about 4.5 times faster through water than through air. And then we can look at a solid, and in this instance it's iron. So this will differ with each solid, and the skull is pretty similar to this, not quite as fast, but still similar. And you'll notice that in iron, sound travels 5,120 meters per second, which is 15 times what it travels in air, and approximately 16,798 feet per second. Okay, so velocity, remember, is the speed in one direction, but it's also divided by time. So this is how we calculate the sound velocity. A cool fact, you don't need to know this, it's just a cool fact, and if you ever are watching the Navy Blue Angel flyers or any of the military jets, they can create a sonic boom. And a sonic boom happens when a solid object, such as a plane, is traveling through the air, and it's traveling faster than the speed of sound. So this jet, and these are typically not jets that you fly in for entertainment purposes. They're generally ones that are used in military operations, but they often fly faster than the speed of sound. And so what happens is, as they're moving through this medium, it creates a vacuum behind them. A vacuum has no molecules, and then the molecules rush to fill in where they're voided. And that sound, when the molecules rush in to fill that area, is called a sonic boom. And so I have a quick video that you can listen to a sonic boom. So that's an example of a sonic boom. You can listen to that again on your own if you would like, but you don't have to, and it's pretty loud. So because of wavelength and velocity and frequency being related, it allows us to calculate the wavelength by using the velocity and the frequency. Okay, so the formula for determining wavelength is that wavelength equals velocity divided by frequency. Okay, so I have done the calculations down here for a frequency that is 2 hertz or 2 cycles per second. And we can measure the wavelength both in the standard system and in the metric system. So if we plug in those numbers into our equation, we have 11 equals 1,125 divided by 2. Okay. And that equals 563 feet. And if we do it in the metric system, we can divide 340 by 2. And we get 170 meters. And these two are equivalent. One is in our American system, and the other one is in the metric system. All right, so what I want you guys to do, and we'll talk about this on Wednesday, I want you to calculate the wavelengths of each of these frequencies. Okay, so 1,000, 2,000, 5,000, and 1,000. Okay, so you're going to use that formula, wavelength equals velocity divided by frequency. Okay, and you can feel free to use one measure over the other, or you can even use both. And I want you to note what happens to the wavelength as our frequencies get higher. So this is a lower frequency, this is a little bit higher, and even higher yet. So what's the difference in wavelength between 1,000 hertz, or 100 hertz and 1,000 hertz? Then I want you to determine what would happen to the wavelength if we change the medium. So if we change the medium from the gas medium, which is the medium that we use to communicate, to a liquid or to a steel medium, what happens to the wavelength? Okay, so this is going to be your homework for the evening to calculate the wavelength and what happens when what happens to wavelength when you change the medium.